Okay, chapter 26, part 3. We have now talked about the differences between chi-squared tests for homogeneity and independence. So now we're going to look at a few examples of running these actual hypothesis tests. You definitely want to make sure you have a calculator. A lot of this stuff is heavy calculator work. So just a quick recap, remember that when we're looking at our chi-squared test of homogeneity, we're looking at just one categorical variable measured on one or more populations. So this was looking at two groups. And we're asking ourselves, are the groups the same? Chi-squared test of independence, we had data from just one group, but we are measuring maybe two categorical variables or three categorical variables. And we're asking ourselves, are the variables independent? Okay, so example 1 says, does attending a particular college within a university lead to different post-graduation activities? The following was collected from a random sample of seniors in each of the colleges at State University. Okay, in the data, it looks like we're given the different colleges that people attended. So these are the colleges within that university, and then these are their post-grad activities. So they're either employed, they're in grad school, or something else. Okay, now it doesn't really tell us much. It just says, does attending lead to these different post-grad activities? We are going to run a hypothesis test here, and what's nice is we can still use our acronym PHANTOMS. So P is standing for what happens in the population. Just like we did with chi-squared goodness of fit, I'm going to, for P, just kind of rephrase what I'm looking at. So in this example, we're asked the question, does attending a particular college within the university lead to different post-grad activities? So we're essentially looking at these different groups here, and we're trying to figure out, are the post-grad activities the same in each group, or are they different? So the way that I would say that is, are my post-grad activities different between the colleges? And you can phrase that a few different ways, but that's essentially what we're trying to find out. Are these post-grad activities the same across each of our colleges? Okay, we still are going to have two hypotheses, our null and our alternative. Now, if we're asking the question, do we think that these post-grad activities are different between the colleges, we're going to start with assuming that they are going to be the same. So I am going to say, for my null hypothesis, that the distribution of post-grad activities will be the same across all colleges. So I'm going to assume that it doesn't matter if you were in engineering or if you were in social science. I'm going to assume here that the kind of distribution or the alignment of employment versus grad versus other is about the same. Alternatively, we'll try to show that this distribution of post-grad activities is not the same. In A, we are going to check our conditions. What's nice is these are the same conditions as we saw for our chi-squared goodness of fit test. So the first one is that we need to make sure that our data was random. This does say that this was a random sample of seniors. So I'm going to just say random. My next condition is that I have categorical data that's given to me in counts. So these are all counts, there's just 305 people that were employed from art and sciences. So I'm going to say that data is counts. The next thing that I need to look at is that my counts are independent. I'm a little iffy on this one because I do think that some students could have majored in, both engineering and social science, so it's possible that people are falling into two of these categories, but for the sake of the problem, I'm going to assume that our counts are independent. My last condition is that I need to make sure I have at least 5 in each category. It looks like I definitely do there. So at least 5 in each category. Okay, now N, we kind of should have started with this part here, thinking about what type of test we're looking at. If the question that you're asking is whether these activities are different between our groups, so different between the colleges, this is a chi-squared test of homogeneity. Okay, I usually think about this right off the bat, so you'll see on some of my answer keys, I write just like right off to the side here. I would have noticed the question says, does attending a particular college lead to these different activities? So that's kind of leading me to believe that these are different groups here. You can also find it by this sentence. It says the following was collected from a random sample of seniors in each of the colleges. So that means that they went to all of their agriculture students, they looked at a random sample of seniors, collected this data. Then the next thing they did was looked at their art and sciences students, they collected a random sample of seniors in that group. Since we're pulling this data from each of these groups separately, it's telling me that I have multiple groups. So if I have those multiple groups, it definitely has to be your test of homogeneity. Okay, here's where things get interesting. Okay, finding our test statistic and our chi-squared and finding our p-value. Now, if we look back at our data real quick, we have all kinds of stuff happening here, right? Like, I don't know if I should type MI agriculture into list 1, arts and sciences into list 2. I mean, does it really matter which one I put where? So what we're actually going to do is use a matrix. Now, if you've taken pre-calc, you may have seen matrices before, but what a matrix does is it looks like this, and you're gonna have just like a bunch of numbers in both columns and rows. So I might have, I'm just gonna do a really easy one. I'm gonna do 2, 1, 3, 5. All right, this is a 2 by 2 matrix. What we want to do is type this data into our calculator as a matrix so that we can run this hypothesis test. So in our calculator, what we're going to do to get to our matrix is we're going to hit second and then x to the -1. You'll see blue above it that says matrix. So I'm going to go ahead and hit that, second matrix. Now, once you're on that matrix button, it's going to start with giving you all of the names of possible matrices. We need to edit, so we're going to go all the way to the left here on edit, and I'm just going to start with editing matrix 1. Now, right now, mine is a 5 by 2 matrix. That means that I have 5 rows and 2 columns. Looking at my data here, I need 3 rows, so I'm going to change this to 3, and I need 1, 2, 3, 4 columns. Now it does spread out these values quite a bit, so right now you can't really see that there's 4, but there are 4 as you scroll. So let's go ahead and type in our data here. I usually just go straight across because if you hit enter, it's going to jump you to the next cell to the right. And then I just work my way down, typing this data into the matrix. Once your data is into that matrix, we can now run this hypothesis test on our calculator to find our chi-squared. So we're going to go to Stat, Tests. I'm going to scroll up, and we are going to click on this chi-squared test that's right above your goodness of fit test. Now, it does not matter whether you're running a chi-squared test of homogeneity or a chi-squared test of independence, you're still going to click on this chi-squared test. Every single time it's used for both of them. So I'm going to press enter there. I have my observed data typed into matrix A, so I'm good there. I can leave that. Your calculator is going to find your expected values for you, and it's going to save it into matrix B. Let's go down and go to calculate, and it's going to give me two important things here. It gives me the chi-squared value of 54.51, so I'm going to go ahead and jot that down for T. For O, I know that I need to obtain that p-value, and it does give me the p-value. The other thing that I need for O is I need the picture. I don't have the picture yet, so I'm just going to kind of draw a template there to save my place, but I am going to jot down this p-value right now. P-value it gives me is 5.82. Please note that there is that e negative 10, so I'm multiplying this by 10 to the negative 10th power, which means I really have a very, very, very small p-value here. Okay, I'm going to go back and run this chi-squared test again. So I'm going to go to Stat, Tests, chi-squared test. I am just going to change this to draw though, so I can see the shape of my distribution and my shading. Now it does look like there isn't any shading here because that p-value is so dang small, but I do like to add it in, so I like to label this as 54.51. That's my chi-squared. And then there's really, really, really small p-value there that's shaded in. Okay, I do want to show you how your calculator saved the matrix, the expected values into matrix B. So if we go back to our matrix button, so that second x to the negative 1, and we just go down to B and hit enter. Once you hit enter again, you're going to get all of these decimals here, which will show you all of the expected values. So this is what we would expect to happen if the null hypothesis was true. So if post-grad activities are the same across all colleges, it's equally distributed across all of these different colleges, these are the values that we would expect to happen. Now, we could find these expected values mathematically. You don't need to find them on the AP exam, so we really won't need that matrix B at all. Okay, we're almost done with this first hypothesis test. Once we have our p-value, the last thing that we need to do is make our conclusion and a statement. Now this p-value is, it's essentially 0. So I'm going to say that since 0 is less than 0.05, we reject H naught. P is so small, we are rejecting that null hypothesis. Okay, if we reject the null hypothesis, that means that we have evidence to suggest that our alternative hypothesis is true. So this means we have evidence that the distribution of post-grad activities is not the same across the colleges. So we have evidence to suggest that the distribution of post-grad activities is not the same across the colleges. Okay, so again, this is a great example of our test of homogeneity, where we're looking at the differences or the similarities between groups. So if in the very, very beginning you're like, hey, I wonder if there are differences or differences between these groups, then we should be running our homogeneity test. Your null hypothesis should always say that the variable we're looking at is the same between these two groups or the same across these two groups. Your alternative hypothesis will be that it is not the same. Okay, let's go ahead and look at another example. Okay, example 2 says a study from the University of Texas Southwestern Medical Center examined whether the risk of hepatitis C was related to whether people had tattoos and to where they got their tattoos. Hepatitis C causes about 10,000 deaths each year in the United States, but often lies undetected for years after infection. So in this case, what we're trying to do is figure out if hepatitis C is related to tattoos and where they got their tattoos. Okay, that word relate there is telling me that I should probably run a test of independence. Another way that you could think about this is when we were collecting our data, I probably didn't split people up into two groups right off the bat. I probably just went up to people and said, hey, you have a tattoo. Okay, let's write that down. Where'd you get your tattoo? All right, awesome. You got it at a tattoo parlor. Oh, and you do not have hepatitis C? Awesome. I'm going to put you in this group here. This probably came from just one group of people. And within that one group, we're asking them two questions. Do you have a tattoo? And where did you get that tattoo? And do you have hepatitis C? Right, versus that last example that we just did, we collected data from multiple groups, which was telling me to run the other test. Okay, we'll go ahead and start with our phantoms here. Okay, in my last example, we asked the question, are these activities different between the groups? Well, I only have one group of people here now, so I'm not really looking for a difference or a similarity. Instead, what I'm looking for is some kind of relationship or association. So for that question, I am going to say, is hepatitis C associated, or you could say related, to tattoos / I'm just going to say where you got a tattoo. Man, spelling is very difficult. Now you could word this a few ways. You could say, is hepatitis C related to your tattoo and where you got your tattoo? That would be totally fine, as long as you're noticing that we're looking at these two different categorical variables, whether or not you have hepatitis and where you got that tattoo. Okay, for my null hypothesis, I am going to assume that hepatitis C is not related to your tattoo or where you got your tattoo. So I'm going to say hepatitis C, how do I want to say this, and tattoos. I'm just going to say are independent. Okay, independent means that they are not related. Okay, they're not related or not associated. That means it wouldn't matter whether I got my tattoo at a parlor or somebody else somewhere else. It's not going to impact whether or not I have or get hepatitis C. Okay, alternatively, I'm going to try and show that they are dependent. So I'm going to say that hepatitis C and tattoos are dependent. Dependent means that they are related, or you could also use the word associated. Okay, A and phantoms here, still standing for my assumptions and conditions, and they're the same as they've always been for chi-squared. So we're going to look for randomness. It doesn't say random, so I'm just going to assume that this data represents people with tattoos and without, so I'm just going to say all people. Hopefully they collected a good sample. Okay, our next one is that our data must be counts. These are all counts here, so that condition is met. Data is counts. Okay, I need to make sure that my counts are independent. So I need to make sure that somebody could not be in two groups at the same time. So you cannot have hepatitis and not have hepatitis. You could argue here that people, maybe got one tattoo at a tattoo parlor and then they got tattoos somewhere else. But for the sake of the problem, I'm going to assume that our counts are independent. Last one, I'm making sure that I have at least 5 in each category or each cell here. 8 is my smallest, I definitely do. So I'm going to say at least 5 in each cell. You would say in each category, that would be fine as well. Okay, next up in phantoms is N. This is where I'm naming the test. We kind of already talked about this in the beginning. We said this was a chi-squared test of independence. Again, a few things told me that I should run independence versus homogeneity. 1, this came from just one group of people. And 2, I'm looking for the relationship between two variables. Okay, T and O are some calculator work here. So, wait, is this it? Alright, I'm going to go to my calculator and I am going to type my data into my matrix. Again, to get to matrix, I'm hitting second and then my x -1. I'm going to go to edit. This is a 3 by 2 matrix. Then I'm going to go ahead and type my data in. Okay, once I have that data typed in, I can go ahead and run my test. So I'm going to hit stat, tests, oops. Going to chi-squared test. My observed is an A. I like to go to draw right away sometimes because it gives me my picture. It's going to give you chi-squared and it gives you P. So my chi-squared is 57.91. You're probably noticing that this picture looks a lot different. It's like real weird looking, very, very, very skewed. The reason that that's happening is because you have less columns. This time we only have 2, so your degrees of freedom are quite low. Again, I don't see any shading there, but I'm going to add it in. And my calculator gave me the p-value of 0. Now, if you're like me, I don't like that. I'm like, 0? What do you mean? It can't be like literally 0. So what I like to do is go back. If it's 0, I usually go back and just run that hypothesis test again in my calculator. Go to calculate instead of draw. And that's going to give you a more precise p-value. So really what this is 2.66 times 10 to the negative 13, which is essentially 0. But I like to have this. It makes me feel a little bit more confident about a p-value of 0. Okay, I have a very, very small p-value there. Again, it's essentially 0. So since 0 is less than 0.05, we reject H0. Rejecting means that I have evidence. So we have evidence to suggest that, let's go ahead and take a look at our hypotheses again. So I am rejecting the null hypothesis, which means I have evidence that hepatitis C and tattoos are somehow related or associated. Hepatitis C and tattoos are related or associated. I can't say exactly what that association or what that relationship is, but based on my test, I do have evidence to suggest that maybe where you get your tattoo does have an impact on whether or not you get hepatitis C. Okay, what's nice about these two tests, they are so similar. You're still going to get the same chi-squared and the same p-value regardless of which test you run. I personally think it can be kind of hard at first to figure out which test you're even looking at. So really pay attention in the very beginning. Do I have one group? Am I looking for some kind of association or relationship? Pay attention to that wording. If you have that one group and you're looking for a relationship, you should be running a chi-squared test of independence. If you're looking for differences across multiple groups or across just two different groups, then that would be a chi-squared test of homogeneity.